Oh, Gaussian is the host. Okay. Yeah, he's right. We have to be sending.
I'm recording now.
Excellent. Okay. So we'll start in a minute or so.
I can see in the list of participants, there's some people I know.
Good morning, Hannes.
Hi,
Good
Mark.
morning, everyone.
Hey, Mark.
I'll keep my video off. I have a lousy connection.
Yeah, okay, just a second. Okay. Okay, Gaussian. So do you want to introduce Hannes or should I?
No, you should. I mean, you invited him.
So,
I'm going
good
to
morning.
disappear pretty soon. I mean, at least on the video.
Yeah, okay. Okay, so if you're recording, you should put the speaker view so we see Hannes in the record. So hello everyone, good morning. Welcome to today's installment of the CGGC Zoom seminar. Today we have Professor Johannes Wallner from UT Graz, who has agreed to give a talk. Professor Wallner finished his PhD in '97 from TU Wayne with Professor Helmut Pottmann, and since 2007 he's a full professor for geometry at TU Graz. He works on computer-aided geometric design, and later he has started a collaboration with Nir Adin on subdivision processes for nonlinear data. He's also interested in discrete differential geometry and applications, for example, in freeform architecture and mechanical metamaterials. And this talk will be presented in SIGGRAPH Asia in a month or so. Go ahead, Johannes. Thank you for joining us.
Yeah, thank you, Miri, for inviting me and for the nice introduction. I'm going to talk about freeform quad-based Kirigami. That is joint work with Caigui Jiang, Florian Rist, and Helmut Pottmann from TU Wien and also Gauss. So what am I going to talk about? So about quad-based Kirigami structures, their geometric properties, their computation, and of course I will also give some examples. So I should say first a few things about origami and Kirigami, about these two words. So origami is very well known. It means the folding of paper, and it has been practiced for a long time. There is, for example, even a textbook from 1797. It has been the object of extensive theory also and of algorithms. And I'm particularly mentioning the paper by Tachi, 2010, what is called the Origamizer. It's basically an algorithm where you can fold any shape. You can see the result by means of the bunny here. So what you do is on a two-dimensional sheet of paper, you just arrange folds that when it all comes together and is folded up into space, the excess material disappears, so to speak, in cracks between triangular faces. And this is a nice theoretical result to have, that you can fold any shape, and what is more, you also even have an algorithm to make it work. There is developments in folding paper, and one of them is curved folds. And I'm showing here a sculpture by the two Demains, by Eric Demain and his father. The reference here is a paper And what they have been doing here is they are drawing two concentric circles and considering the annulus-shaped domain in between. And they do ridge and valley fold along those concentric circles. And then by these curved folds, the resulting object curves into space and you can create really nice things with it. And I'm mentioning this in particular because only this year, Leonardo Alese from TU Graz has managed to show, mathematically show existence of these surfaces where in practice existence is known because you can make them. But it was not known before if this existence is just due to some small buckling or superglue or whatever. And the lesser known brother of origami is Kirigami. It means, literally, it means the cutting of paper. But what is meant is cutting and folding of paper. And I'm able to quote the same textbook from 1797 because it not only has origami patterns in it, but also Kirigami. And the reason why Kirigami has become interesting is because it can model microstructures, or what is called mechanical metamaterials, especially oxetic ones. And I'm happy that Mark is in the audience because what I'm showing here is a paper by Mina Konakovic and co-authors that has been done in his group. What they've been doing is cutting slices into paper, and basically they follow hexagonal regular combinatorics, and by deviations from the regular pattern, they are able to do the pattern in such a way that when you pull at it, you get a three-dimensional surface. For example, this shoe that is shown here. And when you pull at such a thing, it expands. The holes become bigger. And this is what is meant by the oxetic property. So usually in continuum mechanics, in engineering, when you have materials and when you pull, then it doesn't become bigger. It becomes longer but thinner at the same time, so that the volume is preserved. And materials that expand in all directions when you pull at them, they are counterintuitive. They are called oxetic materials, and they also occur really, but this is a special property of a material, and this expansion is caused by some nanostructure that is a little bit similar to these small structures that are cut into the paper here. And what we have been doing in our paper is again Kirigami, and again a mechanical metamaterial, but it is a bit different from the one that Mina Konakovic and co-authors considered. It is not triangle based, it is based on quads, and I'm now going to show what we have been doing. So our aim is to achieve free forms. So general surfaces should be achieved. We want a watertight surface representation. So this is already different from the previous. So we cut holes into two-dimensional material like paper, and then we fold it. And the result is without holes. So by folding this up into space, the holes disappear. And the whole thing is based on orthogonal curve network. So you could also say that it is based on mappings between surfaces. But in contrast to the EPFL group's work, it is not based on conformal mappings, but it is based on general mappings between surfaces. The computation is done by global optimization. What you can see here is an example. So you have a two-dimensional unfolding. You cannot probably see really what is going on unless you look into this subfigure, which shows a close-up. And then this is folded up into space. And this pattern changes so that all the holes disappear. And when this happens, we get this union of boxes. The local structure of such a Kirigami pattern is as follows. So we use as a primitive a so-called box. A box is combinatorially a cube with one face missing. And what we do with those boxes is we consider a base mesh, a quad mesh, and we replace all faces by boxes. So what you can see here is a quad mesh that is very small, only 2 by 2 faces, and each face is replaced by such a box. All of the faces are required to be flat, to be planar. Only the original face of the base mesh that is replaced by the box. There is no condition on that. It does not have to be planar. And the unfolding works so that all edges emanating from the blue faces on top, we cut along those edges that emanate from the blue faces on top, and we get a two-dimensional unfolding. Now, this is possible only if the dimensions of this union of boxes are right. You cannot just unfold and you get a closed unfolding with an 8-sided hole in place of the original central vertex. When you start with unfolding one box, you can of course do it, and then you can go to the neighbor and the neighbor and the neighbor again, and then you have a closure condition so that you can go all around this central vertex. But when you count how many degrees of freedom there are in a union of boxes and how many constraints there are that express that the unfolding closes, there is a sufficient number of degrees of freedom so you can be sure that by some global optimization you can compute a union of boxes like the one shown on the left-hand side that really unfolds into something two-dimensional once you cut open all the edges emanating from the blue faces on top. You can do quite a lot of variations of these basic principles. So, for example, we called the previous one B Kirigami for box, and this one CB for checkerboard box. So we could, for example, replace not all the quadrilateral faces of the base mesh by a box, but we could replace only half of them in a checkerboard pattern. So when we unfold this, the original faces that are shown in yellow, some of them remain, and the unfolding looks different. Now we have, if we again cut open or along all the faces emanating from the, if we cut open along all the edges emanating from the blue faces on top, there is only 2 edges that are incident with the central vertex. So the unfolding has not an 8-sided hole as previously, but only a 4-sided hole. When you count your degrees of freedom, you immediately see that this checkerboard box Kirigami has more constraints, but there are still a sufficient number of degrees of freedom compared to the number of constraints, so that you can be confident that by optimization you can compute such a Kirigami structure. You can constrain it further. So, for example, we can do a checkerboard box Kirigami of the previous type. So you have the quadrilateral base mesh. We replace some faces of the base mesh by boxes, and we do this in a checkerboard pattern. But as an additional constraint, we say that boxes that are immediate neighbors, they must share an edge. And when you now count degrees of freedom and constraints, you see that those numbers are equal. And you cannot really be sure that you can compute such a thing by optimization. And in fact, yeah, we were a bit disappointed that we could not prove existence of such a Kirigami structure in other than trivial cases. So this seems to be at least not immediately easy. But perhaps somebody who looks at this in a different way will immediately have some idea how to prove existence of a bigger type C Kirigami as shown here, together with its unfolding, but at least we were not able to do it. This Kirigami structure that represents a surface is not smooth. It's a kind of corrugated representation of such a surface, but nevertheless, there is a smoothness in the pattern. So for example, the original edges from the base mesh that are still there in the Kirigami structure, they should be fair in a certain sense. So you can write down some fairness functional, some sum of squares of divided differences that should be small in order to achieve a fair curve network that is followed by the Kirigami structure. And also the heights of boxes should be not arbitrary, but they should vary in a kind of gentle way. So when you, by optimization, compute such a structure, you should also impose some fairness functionals on the height of boxes. This is actually a photo of a Kirigami structure made from paper. So the unfolding pattern has been imprinted on the flat sheet of paper by laser cutting, and then this has been folded into space. We can even make the highly constrained type C Kirigami. Here we can see that the side faces of boxes that are kind of orthogonal to the base mesh, they form an unbroken, along the edges of the base mesh, they form an unbroken sequence of flat quadrilaterals that are kind of orthogonal to the base mesh. And this is a discrete developable surface that is orthogonal to the base mesh. And when you think of differential geometry on the properties of surfaces and developable surfaces, you know that if a developable surface intersects another surface orthogonally, then this intersection must be along a principal curve, principal curvature line. So such type C Kirigami can follow, if you have this orthogonality, only the network of principal curves. So this brings me to a major point. You cannot hope to compute such Kirigami structures simply by optimization. You must think of, at least if some fairness is present, you must think of what kind of continuous object is approximated by these discrete objects, and you have to initialize your optimization from those continuous objects. So for example, the type C Kirigami must be initialized from the network of principal curves on a surface. Otherwise, you cannot hope for optimization to succeed. The more general box Kirigami, where you do not have so many restrictions, so many constraints put on it, that can be initialized from a more arbitrary curve network. This already brings us to the problem of computation of such structures. So we start with a cross field or a curve network, which is equivalent because there is standard procedures to compute the curve networks from cross fields. And there is also standard procedures to generate a base mesh that follows that cross field or curve network. So the first step is that we generate a base mesh from this cross field or curve network. The curve network can be seen as the designer's choice. And we can just build a Kirigami structure on top of the base mesh without knowing that when cutting, when slicing it open in the way described, there will be an unfolding. So directly from the base mesh, we can get an initial guess at the Kirigami structure. We also have to initialize the unfolding. And for that, allow me to go back a few slides. So such a box has certain dimensions. It has a height, it has some inclination angles for the sides, it has the shape of the quad at its base. And those parameters determine what the unfolding looks like. It will be inscribed in a bigger quadrilateral. And you could say that the mapping that transforms the base mesh to the unfolding is a locally expanding mapping that maps a base mesh to another base mesh whose vertices are in the center of the 8-sided holes of the unfolding. And you can compute the factor of expansion from the local geometry of the box. So what you do to initialize your base mesh is you just assign new edge lengths by those factors to your given base mesh, and then you can compute an as rigid as possible two-dimensional version of it, and that is now your initial guess at the base mesh associated with the unfolding, and in a second step, initial guess at the unfolding. And this you can throw to the optimization now. So we have hard constraints, that is equality of many edge lengths. And we have soft optimization targets, that is energy functionals that penalize sum of squares of second differences. So those energy functionals are small if the resulting structure is fair. We should also, because we required planarity of faces, we should also add a hard constraint on planarity of faces, but this is actually done implicitly by also requiring equality of diagonals in quadrilaterals. And this, in this way, we can express the isometric unfolding property between quadrilaterals that occur in the Kirigami structure capital M and the flat quadrilaterals, the 2D in the 2D plane quadrilaterals that occur in the unfolding. We express equality not only of edge lengths, but also of diagonals. And in this way, we express the isometric property between the spatial state and the unfolded state, and also the flatness. Because if 4 points with their 6 distances between them are isometric to 4 points in the plane, then they also lie in a plane. So we do not have to express the planarity as an extra hard constraint. It is sufficient which we do everything with edge lengths. The optimization itself is just a standard procedure. So there is nothing fancy about that optimization. And in the end, we hopefully match the cross field or curve network we started from. I forgot to say that proximity to the reference surface is also a soft constraint. Okay, well, some examples. Well, this is of course a very nice example, but it has to be cut open to work. Yeah? So if we have such geometrically complex figures, then we cut it open along a certain mesh polyline, apply the procedure, and we were surprised that we can achieve success to this extent. So this is nice. You can also see how well the planarity of faces is achieved. So what is shown here is for each quadrilateral, the ratio distance of the diagonals in space divided by characteristic average edge length of the quadrilateral. I think I should show you at this point the video, which has more examples. And what you can also see by means of the video is how much larger the unfolding is compared to the three-dimensional structure, which is something that is not so clearly shown in the images. This is another kind of Kirigami, which I was not mentioned in my slides. Here the blue faces form an unbroken surface. This is some architectural design. This one too, it shows that you can have a non-trivial topology. Okay, so this is not thank you yet for the talk. This is just thank you. This is just thank you for the video. In the area of mechanical metamaterials, there is something that is called programming curvature. So when colleagues from materials speak of two-dimensional patterns, origami or kirigami patterns or something else, and those patterns are usually built, those patterns are based on some regular tessellation of the plane. Now, in our case, that would just be quadrilaterals. And in the work by Mina Konakovic, that would be regular triangles or hexagon. And the deviations from the regularity, this is how achieving general shapes is possible. And this is called programming curvature in the materials community. So I'm going to deviate a little bit and show, at least for special Kirigami patterns, how we can read off curvature directly from the unfolding. Now there is the theorema egregium by Gauss that says that the Gauss curvature is an intrinsic property. It is unchanged when you deform a surface isometrically, and you must be able to compute just from arc length of parameter lines. Now, in a discrete version of the theorema egregium, you should be able to compute the Gauss curvature just from edge length of the unfolding, which is indeed the case, because in our case, because we follow an orthogonal curve network on surfaces, we have the easy explicit version of the theorema egregium. It's just if A and B are the derivatives of the parameter lines, so the speed with which the parameter lines are traversed, we have AB times Gauss curvature is some derivatives of those A's and B's. And of course, the edge length in a discrete version of such a surface can be interpreted as discrete versions of those speed with which the parameter lines are traversed, and the derivatives just go to finite differences in the one or the other direction. So we have this expression that for L1 and L2, that is the edge length in the two different directions in the mesh, we have the relation with Gauss curvature. Now that is just a numerical approximation. This is not Gauss curvature in the sense of discrete differential geometry. But we have that too in another kind of Kirigami, what was not defined on my slides, but you could see in the video, and you can see again here, where the blue faces on top of the boxes form an unbroken surface. We can even see the discrete Gauss curvature that is, as usual, defined as 2 pi minus sum of angles in the vertex as angles between edges of blue faces, and for some finite subdomain that consists of a union of quads, you can express the total Gauss curvature that is concentrated here, that would be the integral of Gauss curvature, as a sum of angles between blue faces along the boundary. So this is a very nice discrete version of the Gauss-Bonnet theorem. Let's go back to examples. We were also thinking of what is called here efficient use of material, how to make holes in the two-dimensional pattern small, or how to make the boxes that compose the Kirigami structures of small height. Well, the unfolding process is a discrete version of a mapping between the surface and the two-dimensional domain, and the local factor of expansion directly corresponds to the height of boxes. So if you are given a shape and you want to represent it by a Kirigami structure where the holes are small, where the boxes are small, you have to use an as rigid as possible mapping, so a mapping that is as isometric as possible. We have also been playing around with curved folds. Here you can see yet another kind of Kirigami. It's a checkerboard Kirigami, and Well, here the faces of the base mesh that remain are shown in blue. In all the other slides, the blue faces are the ones on top of the boxes, but here they are not there. So this is a Kirigami where the previously blue faces on top of the boxes are, all the edge lengths are zero, so they are not there. This is a kind of pyramid Kirigami, just to show that we can. And then you see the unfolding, not to scale. Then we applied subdivision to this to get a curved pattern. And then we used previous work to generate a three-dimensional structure that is based not on cutting and folding along straight edges, but along curves, and which does not consist of a union of flat quads, but consists of a union of developable surfaces. There is actually a basic question. Is it possible to achieve Kirigami structures with curved surfaces, but such that you cut along straight lines? The question is our requirement that the faces of boxes are flat really necessary? The answer is yes, it is. So if the cuts and folds are along straight lines, then really all the faces of boxes in our Kirigami structure have to be flat. And the way we can see this is as follows. So a straight cut is a geodesic, a shortest curve. And when isometrically bending and folding this into space, shortest curves remain shortest curves, so they remain geodesics. And we know from differential geometry, we know properties of geodesics. So if the geodesic is a curve, if it's not straight, then it has an osculating plane, and the osculating plane is orthogonal to the surface, to the tangent plane of the surface. So you can say that the surface's tangent plane is uniquely defined by the curve itself. So such a curved geodesic can never be the location of a sharp angle in the surface, because the tangent plane is determined by the curve. And if you have two surfaces, one to the left of the curve and one to the right of the curve, they must share the same tangent plane. So definitely, if a straight cut or fold in 2D is isometrically mapped to space, it cannot represent a curved sharp angle between two smooth surfaces. So the only possibility is that we have straight boundaries for all our faces in the spatial Kirigami structure. And the question is, are there developable surfaces that are non-flat, that allow straight boundaries all around? And the answer is no. You can have, of course, straight lines on developables. I mean, the developables are famous for having straight lines on them, but not all the way around, not on all four sides of the boundary. So for this reason, straight cuts imply flat faces, and we are right in requiring that our Kirigami structures are a union of flat quadrilaterals. We were also thinking of applications. Now, making such Kirigami structures from paper, it can be done. It's not so easy. So if you sit at home with your knife and ruler and you want to make it yourself, this is a bit difficult. But if you can do laser cutting, then it can be done. Yeah? So small scale applications should not be a problem. Medium scale applications like this made from plywood and covered with felt, they are also not that much of a problem if it's not so big that it cannot be handled by one person. So we were thinking by means of these applications, which is actually periodic. You can tile the plane with this element. This is an element for a suspended ceiling with acoustic dampening function for some really fancy installation where somebody has much money to pay for all this cutting and folding thingy. But it must be admitted that on the architectural scale, this cutting and folding is not does not make sense as a fabrication tool. Yeah. So it could be used only as, say, as a design language, which has actually been done in the past. Okay, to conclude, so what have I been presenting? So it's quad-based Kirigami. We were producing watertight surfaces with our two-dimensional cut and fold pattern. The Kirigami and its unfolding is a discrete version of a mapping from a three-dimensional shape to 2D. And because of our design requirements that we have at least approximate orthogonality between the curve networks or polyline networks that govern the shape of the Kirigami and its unfolding. It is actually a discretization of the principal distortions of this mapping to 2D. So it's the unique orthogonal curve network that is mapped by this mapping to another orthogonal curve network in 2D. Special kinds of such Kirigami structures relate to discrete differential geometry. I mentioned that the checkerboard Kirigami have to follow the principal curves, and we also had some nice relations to Gauss curvature, and there is also some more relations that are in the paper, which actually the citation you can find here. It is going to appear in the Secret of Asia Proceedings volume this year. Thank you very much. This is what I wanted to tell you.
Thank you, Hannes. Somebody suggested at some point that everybody unmutes themselves and clap, and that would be nice to get some feedback. You know, it's really hard on Zoom. So thank you for the very nice talk. If people, oh yeah, go ahead, clap. If people have questions, feel free to unmute yourself and ask, or just put it on the chat, whatever you prefer. I can start with a question. So you've shown some examples where actually the combinatorics of the curve network is important, right? So the question is, but from your pipeline, it seems like you start from some given initial quad mesh. So is it possible to write down the optimization constraints that will give you a quad mesh which is good for the various Kirigami that you do? For example, here, like, can I find automatically the best quad mesh?
Not really. Optimization is not powerful enough. So if you impose more constraints, like this, that neighboring boxes must share an edge, so that you know from the theory that this must follow the principal curves on a surface, then your initialization must be like that. Otherwise, optimization does not succeed. Mm-hmm. These optimization tools, they are not powerful enough to find the right combinatorics and so on.
I see. And perhaps another question, you've shown the example where you end up with a smooth surface, right? So the blue boxes made a smooth surface.
Yes.
And so there you said the constraint is for the faces to be planar, right? What was that?
No, where is it? Sorry.
Yeah, it was, I think, one of the last ones that you've shown.
This one, yes.
Yes, yes, this one. So can I take any planar mesh, like any mesh where the faces are planar, not necessarily quads, and generate such a structure?
Good question. I think that this closure of the unfolding, it definitely works better for
quads.
My feeling is it will not work. My feeling is that quads are important.
Mm-hmm.
Now this is, you also have some theoretical side conditions here, because here the surface is discretized as a union of flat quadrilaterals. And if fairness is there, then this should follow a conjugate curve network, of which the principal curve network is a special case. So if you have orthogonality, you have the principal, and if you don't have orthogonality, you can have more general conjugate curve networks. But basically, this is almost the principal curve network, what you can represent in this way.
I see. Okay, interesting. Thank you. So Gershon has a question, and we also have a question in the chat. So maybe I'll start.
Thank you, Johannes. It was very interesting. I have a question actually I can ask in this slide also. I mean, I'm not going to tell you about the application because I know your views about military applications, but I wonder can I modify interactively, like animate in real time the blue panels, even by minute amount? And if you think we can do it, what are the degrees of freedom I have to apply to do some kind of motion of individual panels, even minute ones?
I think that the degrees of freedom that you have, so the left-hand figure is looks like parameter lines of the principal parameterization of a surface, and the spacing of the parameter lines corresponds to reparameterization of in one or the other variable. So
right, but I have a physical model of this. The question is, it's already built, so the parameterization is already given.
Yes.
But given the model, I want to tweak blue tiles here, like move them up and down and twist the direction that they are looking at, even in a minute amount. So how would you go about doing that?
If you do not change the reference surface, then the degrees of freedom I have is just the spacing between these polylines. As long as, I mean, if you do not impose fairness, you can do all kinds of things. But if you still have an approximation of a smooth surface and a curve network on the surface, then this, yeah, of course, there are other.
Well, we can talk it offline if you prefer.
I think
discussing military applications.
I think it's rather rigid because if you definitely if you have orthogonality, approximate orthogonality and flatness, you are stuck with the principal curves, and then all you can change is the spacing.
Maybe
interested in if you forgo the fairness, then you have more degrees of freedom. But yeah, then I would use, yeah, I would write this as a system of equations. So variables and equations like the vertices that are there and the surface normals and so on, and write down the equations that express the constraints, and then use this. Yeah, you use this. Was published by Cheng Tang and co-workers in SIGGRAPH previously. Yeah, this looks as if was the right method to change this at close to interactive rates.
We have one question on on the chat again about optimization. Thank you for the very good talk. I have the following question regarding optimization. How can you tell the obtained solution is a global optimum, how the initial guesses are made, and how the global optimum is found? And there are different combinatorial structures to start with. Is there a specific rule of thumb as to how the initial shape is made?
Yeah, so unless we have the more highly constrained Kirigami, so just a box or a checkerboard box, we can start with the orthogonal curve network or a cross field. This is the designer's choice. Mm-hmm. And from this, the initialization is made. So the initialization is the base mesh. You convert the cross field to a quad mesh. For example, using live Cobbolt's paper on derive a quad mesh from a cross field.
I see.
And the degrees of freedom that are available in that stage is the spacing, basically. And mm-hmm. then you still can choose the heights of boxes and the shape of boxes, and then you, yeah, which generates the local expansion factor, and then you initialize the base mesh. You can actually read the paper on my webpage. Yeah, it is there. Yeah, it is no good explaining that.
Do you have code? Yeah, that's an answer.
Yeah. So if there are different combinatorial structures to start with, well, you can just try them out. Yeah.
Yeah.
It is usually not so constrained that you have to use one or the other. And if we achieve a global optimum, well, we have to. The optimum is as far as the hard constraints are concerned is 0. Yeah. So yeah. We can always tell if we minimize the target function to an extent that is required for the application. So deviation from the isometry should be less than so-and-so because you want to make it from paper, and you cannot go beyond whatever, yeah, 0.005 or something. Yeah.
So you have physical constraints that drive the action.
And when you achieve that, you do not care if there is another global optimum that also.
You need one.
Yeah. So you will be able to see that you match the original cross field or curve network. So you verify a posteriori, so to speak. And if you could experiment with different local geometries of the boxes or so. This is what I would do in practice. But since the target, so the optimal value of the target functional is 0 anyway, you can check if you have reached it. But there is no guarantee that you reach it. It's just evidence from doing many examples. There is no theoretical guarantee.
Yeah, it's a difficult optimization problem, so that's
yes.
Not surprising. Okay, so I think if there are no more questions, we will thank the speaker. Thank you, Johannes, very much. And after SIGGRAPH-Asia is over, we will post the video online.
Yeah.
Okay, so thanks everyone again, and see you next week.
Yeah, Bye. Thank you.
Bye-bye.
Thank you.
Bye-bye.
Bye.